Let's get started. Good morning, everyone. Can you hear me? Yes, hear me? Okay, good. Hello again. I'm your host for today's workshop on big data in watersheds, integrating wetlands and floodplains in watershed modeling. First, let me introduce myself. I'm Adnan Rajib. I'm an assistant professor at the Texas A&M University, Kingsville. I received my PhD in civil engineering in 2017, then I spent a little over 2 years at the EPA Office of Research and Development as a postdoctoral scientist working with Dr. Charleston and Heather Golden. By training, I'm a computational hydrologist with a background in hydroinformatics. So what I do is the marriage between informatics and traditional hydrology. Most of my recent works involve large basin hydrologic modeling with specific focus on wetlands and floodplains. Please let me introduce my co-hosts as well, Dr. Chuxing Wu and Tianjing Zheng. Dr. Wu, please introduce yourself. We can't hear you, Dr. Wu.
Can you hear me?
Yes.
Okay. I'm Chuxing Wu at the University of Tennessee. I got my PhD in 2015 in geography. And then I spent 4 years at the State University of New York at Binghamton until 2019. And last year, I just moved here to the University of Tennessee. And my research focused on GIS remote sensing and using GIS remote sensing to map surface water and wetland inundation dynamics. And I also work extensively using Google's engine. I'm very excited for today's workshop.
Okay, Tianjing is my PhD student. Go ahead.
Okay, hi everyone. My name is Tianjing Zheng, or you can call me Stella. I'm a PhD candidate in Dr. Anand Rajib's research lab at Texas A&M University, Kingsville. My research is focusing on hydrological model, especially looking at the effects of wetland and depression storage on large basin water resource. I also develop lots of cyber-enabled tools to integrate geospatial data and hydrological model. I'm excited to be here and glad to see you all, and hope to talk to you more in the next few hours.
Okay. I'm going to share my screen now. And guys, if you need to ask questions, feel free, just interrupt, and you can raise your hand. There is a button on your lower right corner in the chat box. You can raise your hand, and also you can type in questions. Okay. Let me share my screen. There we go. Okay. Can you see my screen, guys? Okay. There we go. I can minimize this. Okay. Big data. Big data is a new buzzword floating around in recent years and constantly seeking our attention. There's a common misperception that big data perhaps refers only to the big size or big volume of data sets. That is not true. When it comes to watersheds and watershed modeling, big data is all about data discovery and integration. Discovery and integration is the essence of our workshop. Okay. Now think about this. As a community, our modeling experience is right, but our skills to dynamically discover and integrate big geospatial data resource and integrate those data resources within the black box structure of watershed models, it's still growing. And there is no question about the gap. There is a persistent gap. And that's exactly the reason why we designed a workshop to minimize the gap between data and models. What we're going to do here is we are going to train you with the skills of data discovery and integration in watershed modeling. For certain reasons, our focus will be on wetlands and floodplains. Okay. We have divided the workshop into five segments. On your screen, you can see those segments and approximate duration for each of the segments. First, we are going to lay out the background, the state of the science, why it is important to have an accurate representation of wetlands and floodplains in models. What are some of the most recent scientific works along those lines? We're going to talk about that. Second, we'll explain why wetland and floodplain integration is a so-called big data problem. So we'll go into the details of the basics of discovery and integration. The third segment is where we become more interactive. This is when we will do a live demo, and you as participants, you will follow our instructions and try a new cyber-enabled tool to integrate wetlands and floodplains in a SWOT model. The final two segments, these are my favorite segments because this is when you run the workshop. Basically, what it means is you are going to tell us what you need and how you want us to assist in your pending research projects or upcoming research projects that might involve wetlands and floodplains. Okay. We'll have fun. By the way, the slides are available for you to download from this link. So feel free to download the slides. It should be available in PDF format, I guess. But anyways, it's available for you to download. Okay, guys, let's begin. First, the state of the science and state of the science of the floodplains. Long story short, watershed models, in commonly used watershed models, floodplains don't exist. Technically speaking, models collect all the runoff from the landscape. And after collecting the runoff from the landscape, the models pour the water at a watershed outlet and then just simulate a horizontal routing with some semi-empirical parameters. Now think about HCHMS. Probably it's one of the most widely used models worldwide. Now HCHMS, when it simulates the routing, river routing, all it does, it uses K and X, the two parameters, mass kingdom K and X. Where is the floodplain in the model? So that's the reason I said in commonly used watershed models, floodplains don't exist. And if you take the example of some of the most advanced models, such as WRF Hydro, situation doesn't change there as well. However, in reality, floodplain hydrology is a function of a lot of things. Floodplain width or extent, the storage therein, and the surface roughness. The question is, how do we make the model understand the location, spatial extent, and some of the physical properties of the floodplain? We'll see. The next one is about wetland and surface depression storage. Wetland and other surface depressional storage systems are basically small, unmanaged water bodies that are part of the landscape fabric. These small water bodies are like small containers or buckets. They hold the water and they delay the movement of water when the water travels downstream. While holding the water, these water bodies also capture sediments and nutrients by settling and some other biogeochemical processes. Unfortunately, watershed models typically do not include these important processes. Models typically do not include these small surface storage features. And why is that? Because there has not been any efficient way to know where these storage features are located and how much water they can store. Unless we know this information, we can't include them in the model, right? So far, there has not been any efficient way to know where they're located and how much they can store. But now we have those capabilities. In the next slide, Dr. Wu will show you how depressional storage systems and their flow path and their upstream to downstream connectivity can be detected. Dr. Wu, can you help me explain this slide?
Yes. So basically, in the past, I think 2 years ago, we published a paper using a graph theory called contour tree to delineate the depression hierarchy. As you can see from the figure on the upper left side, you will see that water can be floating in bidirectional. So it depends on the existing water level and also the rainfall. And we can do simulation to figure out, for example, which depression is going to connect with which depression. So basically, there's a hierarchy on the landscape, and you can figure out the appearance, their brother and sisters. And eventually, with the water level increasing, you will water going to flow from upstream to downstream. And we can also use LiDAR data to delineate the flow path. So on the right here shows you the flow path delineated using LiDAR and the algorithm. So you can see, for example, on the upper right corner, the depression and flow path overlaid on the LiDAR DM. There's a thick blue line around the center. So that one is the flow path from the NHD, so more like permanent water. But those are temporary or intermittent surface water connections were rarely mapped. So we can actually use LiDAR data to delineate those temporary flow paths. And if you overlay those flow paths on the high resolution NAM imagery, see the one at the bottom, lower right, you will see that those flow paths align very well with relatively like pink color. So those are where the vegetation grows, where you have high soil moisture. So essentially, we can use this kind of algorithm and high resolution LiDAR data to map those surface water connections. Either it's permanent or temporary. I will talk about later how to delineate the depressions and also how to delineate the depression hierarchy using the label set algorithm.
Wonderful, wonderful. Okay, thank you, Dr. Wu. So these are the new capabilities which didn't exist a few years ago. And that's probably the reason why integration of these surface storage features and important features such as floodplains has not been developed yet. With these new capabilities, we recently developed a model for the entire upper Mississippi River Basin. The specialty about this model is this model includes the water storage of nearly 500,000 depressional storage features. Now that's a big deal. 500,000 depression storage features, which usually we ignore while we do the model. And this is what we found. The map on your left, it shows the average annual water yield from a conventional model. That's what we do. The conventional model, which does not include the small surface storage features. It's the regular rainfall runoff modeling. It has all those big reservoirs, dams, and calibrated with a lot of gate station stream flow data. That's what we call it a conventional model, because it includes everything else, whereas ignoring the small surface storage features. This is the average annual water, the map on your left. The map on the right, it's the depression integrated model. So you see the exact same model. One doesn't include the depressional storage and the other one includes the depressional storage. And there's a 40%, nearly 40% difference in average annual water rate. Okay? So what do we conclude from here? Models built without surface storage features may not be giving the right answers, or they may be giving the right answers for wrong reasons. Let me stop here for a little bit and see if you guys had any questions. Feel free to ask questions. Okay. Any question, guys? Great. Well, I have questions. So integration of wetland and floodplain in a watershed model is important. We get that. But how is it, how this integration, how this wetland and floodplain integration is a so-called big data problem? Let's talk about it. So this is our second segment where we are going into the details of data discovery and integration and trying to relate the big data concepts with the traditional watershed modeling. So all the data sets that we are talking about here, like the floodplains, wetlands, they are basically part of open access data networks. They're all public domain data sets. And they're interactive maps and interactive map interfaces that you can use to access your desired data set. Now the question is, why can't we download our desired data set and just dump those files inside the model folder? We can just go to the FEMA website, download floodplains, and just dump the floodplain in the model folder. Well, it sounds easy and doable. As I said, all these data are public domain data sets, and there are nice interfaces where you can go and download the data, but it don't work for a couple of reasons. Okay. First, let me explain why. First, you need to find the data such that can you guys hear me? I'm not sure because I'm looking at the screen. Okay.
Yes, we can hear you.
Sure. So as I said, it sounds easy to grab those data sets and just dump it into model folder. And our expectation is that, oh, it should work because we fed the model with the data, but I can explain why it's not going to work. A couple of reasons. First, you need to find the data such that the data are spatially consistent with your watershed. Spatial consistency, number one. Second, the data structure has to be compatible with the model structure. For example, SWOT model, soil and water assessment tool, like I guess many of you are familiar with the SWOT model. SWOT model discretizes a watershed as subbasins, small sub-watersheds, small catchments within the basin. So this is the spatial discretization of the SWOT model, and all SWOT input-output files are basically ASCII text file formats, simple text files that you can open in notebooks, and you can see from the right image in my screen. Okay. But for the same watershed, if you were to create a Warfighter model, your model would discretize the watershed in regular grids, and many of the files used in the Warfighter model will be in netcdf format. Therefore, spatial consistency and structural compatibility, so both are equally important factors. So we can download the data, we can access the data, but that doesn't mean that the data is spatially consistent with our watershed and structurally compatible with our models. Let me explain this in a more organized way. Okay. Let's assume that if you were to integrate the bunch of geospatial data sets in your model, the first step would be data discovery. Now, data discovery also includes finding the data and downloading the data. Now, you may think, well, data download is not complicated. As I said in the previous slide, you will just go to a website, click a couple of buttons, that's it. Well, let me give you one example. I'm good at downloading the FEMA floodplain data. But now you come to me and tell me, Adnan, you can't use FEMA data. From now on, you need to use floodplain data from EnviroAtlas. Well, because you changed the source of the data, the way I used to follow to download the data from my watershed won't work anymore. I will come across the same problem if you ask me to change the model. So data discovery includes data fetching, in other words, data download or data accessibility. Changing in one of the components affects the others. So it's a critical problem. We need to find out ways to make the data discovery reproducible. Anyhow, the next step is data processing. We always need to apply some GIS functions to make the data ready for the model. Remember what I said in the last slide, structural compatibility between data and models. For example, FEMA floodplains are available in GIS as GIS polygons, but water hydro model runs on regular grids. How do you make these two compatible? So there has to be some intermediate steps, processing steps, to make these two talk to each other. Okay. Although some people consider processing as part of data discovery, but we like to keep them separate. Okay. The final step is data integration. This is when you need to play with the model source code, because this is where you are ingesting the spatially and temporally variable data into the model. So you have to make your data ready so that it can be readily blended into the model source code. As I say, all other parts remaining the same. If you change your model, the data integration won't work. So our end goal is data integration, but to make it possible, we have to take care of data discovery and processing as well. Now, the big concern is this whole workflow doesn't seem to be very stable, because change in one affects the others. So how do you make it reproducible? That's the reason this is a big data problem. You have to make sure that everything works in a reproducible way, no matter what you change, but the system will still retain itself, reproducibility. Okay? Well, good news is we solve this problem by automating this workflow and putting it under a cyber physical system. So that's the centerpiece of this problem. If you want to solve this problem, the centerpiece is the cyber physical system. And the name is self-explanatory. Cyber means it runs online, the system is online, and physical means it has a certain degree of intelligence. It can adapt itself. It can run by itself without having to wait for users input. Now, the question is it a hypothetical system or it exists? Well, I have good news for you. It exists. And we have developed a tool to integrate, cyber-enabled tool to discover wetland and floodplain data from open georesources and then integrate wetland and floodplain data into watershed model. Let me outline a skeleton for this cyber-enabled tool, because in the next segment, you are going to run this tool. Okay. The first segment in this tool is data discovery, and all it needs is your SWOT model. In this case, we are considering SWOT as an example. So that's the only input this tool requires from the user, your SWOT model. The moment you feed the SWOT model into the system, you can just upload a zip file. That's it. That's it. And the moment the system finds your SWOT model, it automatically identifies your watershed location, all the geospatial structure, file structure. You remember what I said, like structural compatibility, spatial consistency. So the moment it finds the zip file, it knows where the watershed located. It knows how big the watershed is, the sub-basin structure, the river network, everything. Then it goes automatically to the data sources, because we set a target for this tool, and the target is go and fetch the topography, go and fetch the land cover and floodplain. Because this is the target for the tool. The tool doesn't want you to download the data. As I say, this is an intelligent system, so it automatically goes to the national elevation data set, USGS national elevation data set for topography. It goes to the national land cover data set for land use, and currently it goes to Enviro Atlas, which is an EPA database, national database for various geospatial data. So this tool automatically interacts with this source, and it fetches the data and comes back. That's why there is a two-way relation here. It comes back. Now, when we designed this tool, we wanted to have we wanted to have more flexibility, more modular structure. And that's why we are giving users some option. If you want, you can actually upload your own data set. The reason we did this is because some water districts, local offices, local watershed management divisions, they have some high quality data sets. Floodplains, which are based on survey, land cover, which are based on drones and all that. So we let users upload their own data set rather than relying on open source data sets. So that's a flexibility here as well. If you want, you can just upload your own data set, but the system would still work. Now the data is there. Again, you are not downloading the data. If you are going with the default option, the system downloads the data. Okay. The next segment is the processing. Now the system has all the data, it automatically starts processing. Remember, this could be a computationally intensive work. However, the system doesn't rely on the computer, on your computer. It relies on some web-based cloud computing platform. And Dr. Wu is going to show you what's happening there. Anyways, so with the data in hand, the tool estimates surface area and maximum storage volume of depressions, wetlands and surface depressions. And then it also calculates the floodplain storage. Right now, we represent floodplain storage as the width of the floodplain and a geomorphic property, surface roughness. Okay. So once you have these information ready, the tool calls the model again. First, it called the model in the very first step to understand how the model looks like the geospatial structure. But now all the data set is ready. So the tool will call the model again, and it will feed all the information directly into the model source code. If you want to change the model, if you do not want to use SWOT model, that's fine. The other two components won't be affected. If you want to integrate another model, that's fine. The other two components won't get affected. If you want to change the methodology for processing the data discovery and data integration won't be affected. So that's the essence of Cyber 2. Okay. After all the steps are completed, the tool will let you download the model. The model that you are downloading in the final step, it's a modified model which has all the information, depression storage, floodplain storage, everything there. And then you can run your model offline or using a local computer, because this tool doesn't run the model for you. Okay? It just assimilates the data. Now, you must be thinking this is a hypothetical structure and it doesn't exist, but actually it exists. And good news is you don't have to do a lot of hard work to use this tool. This tool is, it's possible to run this tool using your Gmail account. All you need is a web browser and a Gmail account. That's it. With that note, let me welcome you to Google Collaboratory. So Google Collaboratory is a platform where you can run this tool using a web browser. That's it. Okay. And it's open access and it doesn't even require your computational resources. So when we first started thinking about this tool, we had a lot of questions in mind, and I'm sure you guys also have these questions. Let me share the questions that we thought about. Do I need to learn any programming language to learn this tool? That's an obvious question, right? Do I have to install any software in my computer? My computer is old. It always gives me hiccups whenever I try to install some software. Do I have to install software? Do I have to understand the model source code? That's a big deal, right? Modeling is one thing, and understanding the model source code is a completely different ballgame. Do I have to understand the model source code? And does it work for SWOT only? What if I want to use Warfighter? What happens? The answer is no. This tool is findable, accessible, interoperable, and reproducible. FAIR. So FAIR is the definition of big data. Any big data tool has to be a FAIR tool, and that's what we wanted to achieve here. We tested the tool. After we developed the tool, we also did some testing across 7 watersheds, different watersheds in different geophysical settings across the US. And you can see these watersheds, we varied the geophysical settings as well as the watershed size purposefully, because we wanted to see whether or not there is a relation between the watershed size and the runtime. The biggest watershed that we tested is Wabash in central Indiana, 18,000 square kilometers, and the smallest one looks like Calafia River in South Florida. Now you can see, well, there are a couple of take-home points here. There is no relation between runtime and the watershed size. There are a lot of factors there, the topographic variations, the density of wetlands, sizes of wetlands and depressions, size of the floodplains, all sorts of factors. So it's not linearly related to the watershed size. The second point here is it's really quick. So starting from uploading the SWOT model to the finish line where the tool gives you gives the model back to you, we found that for an 80,000 square kilometer watershed, it took only 20 minutes. Remember, the tool has to download the data, process, assimilate the data in the model. So it took around 20 minutes for the biggest watershed. So that's a pretty good deal. Okay, so with that, we reached the third segment. This is where we expect you to run the tool following instructions. And you will see that the tool is divided into 2 segments: data discovery and integration. Dr. Wu designed and envisioned and developed the data discovery part, and Chen Jingzhen, she developed the data integration part. So Dr. Wu, please take over from here. So I will request Changing first to introduce the SWOT model structure, and then Dr. Wu can explain the data discovery. Let me stop sharing my screen here.
Hi, I'm back. So let me share my screen just to do a bit introduction part. Okay. Does everybody can see my screen? Okay. So in this exercise, we will show you how to discover, process, and integrate data into the SWOT model. But before we before we walk through the tool, it is really important to have basic understanding of the files structure of SWOT model. Just like any other tools, if the format of the tool is offset even a little bit, the tool will raise error or not recognize at all. So the SWOT model is a standardized model. When you create a SWOT model, it will always give you similar structure of files and folders, except the project name. That is to say, the model might not recognize the file and the folder if you have been accidentally modified or renamed it. In a SWOT model, there are 2 important folders: scenario and watershed. All inputs, outputs, and configuration stores in scenario folder, while watershed contains all geospatial files, such as boundary and the river range shapefile. Our tool will detect these folders and extract the information we need to calculate the depression and the floodplain storage. In this exercise, we are going to demonstrate with a SWOT model for the Cedar River watershed in Iowa. Our code is designed to fit any SWOT model. If you want to use your own SWOT model, make sure you zip and upload your model to the Google Drive and change these 3 lines: project zip, project and the floodplain zip URL, and the project root directory. I will let Dr. Wu take over from here, and I will be back with you in a while.
Thank you. Changing Dr. Wu, please go ahead.
Okay, can you see my screen?
Yes, yes, we can see your screen.
Okay, so let me go through. Thank you, Stella, for the introduction. So I'm going to go through the steps how we can delete and load the three files needed for the model. So essentially, at the end of the part one, the data discovery, we are going to have these three files. The first one is the CSV with depression stories. So if you can see from here on the at the first column, we have the subbasin ID. So if you go back to, let me show you in here. So this is the Cedar River watershed we're going to use as an exercise, but you can customize to use any other watershed. And so the gray, it might not be very clear, but you see the gray boundary, those are the subbasins. So in this watershed, we have a total of 95 subbasins. So at the end, we're going to get a CSV with depression stories, the subbasin ID, the first column. The second column is the depression area. So at the end, we're going to aggregate all the depressions within each subbasin. And we're also going to calculate the depression volume. So based on those depression area, we can calculate the stories of each depression and then aggregate the subbasin scale. We also have the basin like the area. So just each subbasin, how big is the subbasin? And the last one is the depression to basin ratio. So basically, what's the percentage of depression area compared to the basin area. The second file is the floodplain width, and so we'll come back later for the depression later. But the floodplain width is relatively simple. So we provide the floodplain raster. So this is the one at the beginning of the code block. You're going to provide three files. So this one is the second one, the floodplain raster. And we also have the floodplain, the river network. So this one comes from the SWAP model, the zip file, and we're going to extract this one. Again, we're going to aggregate the result to the subbasin level. So it will be the floodplain width will be just the floodplain area, the total divided by the total, the stream length, and then you get an average of the floodplain width. So if you come back to see this one, so this is basically just a plain text file, and so each one correspond to one subbasin. So this will be the width represent in meter. And so lastly is the floodplain roughness. So this one comes from here. So we need the subbasin. We also use NLCD, and based on the floodplain, we can crop the data to extract the NLCD just for the floodplain area, and then we do the recording. So from using the NLCD, so this is the lookup table we're using, and to convert basically each lane cover type to a corresponding roughness number, and then at the end aggregate at the subbasin level, get an average roughness. So if you come back to again here, this is the file we're talking about.
Dr. Wu, people has some questions for you.
So how is a depression defined topographically? So this one is we're going to talk about a little bit more later, but it's based on the level set measure. So you can think of this like a sink filling, a depression filling algorithm. So at the end, if you have old water rainfall flooding the plain, so anywhere that's covered by water is going to be extracted as a depression. So it's similar to the traditional algorithm, but it's more efficient. Can you describe the second question? Can you describe how you obtain the data to calculate the volume for these small depressions associated? For this exercise, we didn't handle basically when you have a depression, we have water, you can have potential water storage. We also have existing water storage. So depends on the specific area or region, you can actually estimate the depression existing storage based on the basin morphology. In this example, we don't use that, but I had a paper published in 2016 describing how to estimate the depression storage for porous potholes based on empirical equations. But for the potential water storage, that one we can delineate using LiDAR data or DM. So basically, you can figure out the potential water storage when the water is going to flow out from that specific depression to the downstream. So that one you can use the equation to calculate. I think in the paper I also describe how to actually to delineate the storage, but for this exercise is not as complicated as this. So we will talk about later when we go through the source code. And the other question, has the sensitivity of roughness parameters been done also that affect the peak discharge and its timing? Anand, can you handle this question?
Yes. So I assume it's about floodplain roughness. So we use standard literature to assign a specific roughness value for each of the land use category. So what it does is our tool finds out the land use within the floodplain extent. Even if the floodplain is variable, it doesn't matter. It finds out the land use, and for each of the land use category within the floodplain, it assigns a static Manning scan, and that is based on some standard literature. We didn't do any sensitivity analysis for Manning scan, because that part goes into model calibration, honestly. But we just assign a static Manning scan to the floodplain and then let the model calibrate itself.
Okay, so next, this goes through the source code. I already put, let me put the link here again in the chat box. So you can click the link. From there, you should be able to open the notebook on your browser. If you have any issue, you can unmute yourself to ask. So feel free to stop me if you run into any issues. Can you still see my screen?
Yes.
Okay. Yes. And once you are open, probably you need to log in using a Gmail account. So I'm going to give you a couple seconds to log in, because if you don't log in, you won't be able to execute the source code. And once you open the notebook, on the left side here, I'm going to show you to go through like some of the key things you need to know in order to run this notebook. On the left side here, you will see a couple buttons. So upper left corner is a table of content. So on the left side here, for me, I'm going to focus on part 1, and you will see from step 1, 2, 3, all the way to step 14. So I'm going to go through step by step. Also, there's another button at the here, the folder icon. So these are the two ones that you need to know because later we want to look at the files associated with this. And you can also mount your Google Drive. For now, if you probably only see the sample data because I already did mount my Google Drive. If you want to mount your Google Drive, you can click the icon here. Click this one. You will mount your Google Drive. You're probably going to generate a code block in here, and then you need to execute. But for this exercise, you don't have to do that. So it's optional. You don't have to worry about it right now. But I will show you later. The point of mount your Google Drive is for you to copy data from, keep it in mind, everything right now we're running is temporary. So if you close the browser, you'll be gone. So make sure that, also, by the way, when you open the notebook, probably somewhere here above, there's a text showing the copy to my Google Drive. Can you see that one? Because this one is already in my Google Drive, so I don't see that one. So I recommend that you copy the button, click the button, copy to my Google Drive, and it's going to copy the notebook to your Google Drive. By default, it's going to be create a folder named Collapse Notebooks. So you should be able to see this folder, and you will generate a file directly under the Collapse Notebooks. Any issues? once you copy the file, so anytime when you're making changes, it will automatically be saved to your computer. So you can see this one, the Google Colab is just another cloud computing platform provided by Google. Just think about Google Documents or Google Sheets or Google Slides. It's the same idea, but this one is just for you to do coding. And also I'm going to show you here, upper right corner, you should be able to see this one here. If you see a green check mark, that means right now your notebook is active, is connected to the cloud computing environment. You will also see this one, the RAM and disk. So basically the memory and the hard drive are provided to you for this notebook. So if you click, you can see, for example, right now we are using 0.8 gigabyte of RAM, and also it has almost 100 gigabyte of hard drive. So everything is temporary. It's sufficient for this example. Any questions? So if not, let's go through the notebook step by step. And before we get into the detail, I would like you to know some of the shortcuts that you need to know, because extensively we're going to do some coding, but you don't have to write any source code, but you need to know how to execute the source code. So if you scroll down in here, if you place your cursor somewhere in a code block, on the left side here, there is a icon. So if you click this one, it's going to run this code block. So if you click, and depends on how computationally intensive of that code block, it might take a while. It's going to spinning for a while, but for this one, we are going just defining 3 variables. So it's very quick. You can also double run multiple times. And so the shortcut you're going to use in here, there are a couple of these that will be helpful during this workshop. So the first one is Shift Enter. So basically, if you don't want to click like your mouse every time, you can just use your keyboard. So if we use Shift Enter, it's also going to execute this one and then move your cursor to the next code block. You can also do Control Enter. So Control Enter is going to execute, but the cursor will stay on this code block if you don't want to move the next one. So Control Enter. You can also use Alt Enter. So Alt Enter will create a new empty block beneath. So if you see from this one here. Okay, I'm going to give you 10 seconds to practice. So Control Enter, Shift Enter, and then Alt Enter to see the differences. You can also delete this one if you don't like. But don't delete any other code block, because if you delete any of those, it will become disconnected. So you will be having issues. And the last one will be the Control/. So Control/ is to comment out a line. So sometimes if you have a certain line that runs a long time, you want to comment out, you don't want to run it multiple times, you can have Control/. So for example, for this one, if I put my cursor in here, if I Control/, it's going to turn into green, and you will put a hashtag at the beginning. So that means this one right now is comment out. So this one has no effect. So it's no longer, it's still a code block, but it's just a comment. You can write a description or anything. So this is just a common thing in the Python or programming. And if you Control/ again, it changes back. So then you can execute. Okay, so once we get to know those shortcuts, and then we're going to go through the step by step. But first, Stella already mentioned this one. So for this model, all you need to do is provide these 3 inputs. And so the first one is the project folder. Looks like this. This one comes from the SWAP model. So you need to get this one. And then all you need to do is just upload this one to your Google Drive, and then click share. You probably need to share to the public. So create a public link, and then you copy the link, paste in here. That's it. The reason we're using this one, because right now we are running in the Google Colab. So every file that already in the Google Drive is already in the cloud computing environment within Google. So when you copy the file, it's very, very quick. If you put the file somewhere else, it might take a long time to download the file. So this is the recommended way. And you will need these 2 links. The second one is the Floodplain. All right. So this one also you can download from, depends on where you get this data. You can also join this one using the download from the internet, or you can produce this one by yourself. And this will be a raster file. So you'll be the floodplain raster data set.
Dr. Ru, can I jump in real quick?
Yes. Mm-hmm.
So guys, as I showed you in the slides, the tool is flexible, and we can let the tool fetch the floodplain data for any watershed. And currently we tested the tool for EnviroAtlas and FEMA, but just to make the process quicker, we in this exercise, we uploaded the floodplain in the Google Drive. We are trying to mimic a situation where you already have a floodplain and you just upload a floodplain in your Google Drive. If you don't want to do that, if you want to rely on open source data sources, our tool can do that. You don't have to upload the floodplain. However, you must upload your model, otherwise it's not meaningful.
Okay, so once you get this set up, then everything else is automatic. So you don't have to worry about anything. So if you don't want to go through the source code one by one, you're welcome to go to the menu. If you click the menu, runtime, and you can click this one, run all. Don't run it yet because it's going to take a while. But I'm just showing you that because I'm going to go through step by step. It's going to take some time. But when you already set up your model, when you already have everything, you already know like exactly what the source code is doing. Then you can just run all. So everything else is automatic. And once you click this one, at the end, we're going to get those 3 files: the depression stories, and also the floodplain width and roughness. Okay, so you're welcome to use that one. And the other one you can do is to go to the edit menu. You can clear all outputs, because later we're going to join a lot of output. You can clear them all at once. So right now I will encourage everyone to go to the edit menu and then click the clear all outputs. So you don't, in that way, it will clear the output, because this is a share Google notebook. Everything that you see in here, we are using the same document. If you copy that one to your Google Drive, then it become independent. If you use the same one that I'm using, then you will see all my outputs. Okay, clear all outputs. Then we can start from the very beginning. So first, we're going to execute this one. So this one is simple. So this is the file where they're coming from. And then we pass this one as a variable. And then you execute. So next, we're going to create an output folder. So everything will be under the content data. If you see from here, this one right now is the content folder. So later we're going to create another folder called data, and then everything will be saved to this directory. Let's click this one, okay? And for this one, like I said, it's commented out. You can control / to uncommon if there's already a folder in there. The reason I'm using this one is you might be already running a model and then you join the data, but later you want to run a new model. You don't want to mess up those data sets. You can clear all the directories. But for now, we don't need to execute this one. And next, we're going to install some Python packages. And as you can see from here, we use a variety of packages, and GeoPandas or raster.io or raster state. And we also have the other one called Gmap, LiDAR, and Whitebox. So those 3 packages are the one that I developed, but I also utilize some other packages. So all we need to do is just click this one. And you might also see this one, the double percent capture. So that one, if you control / if you don't use, it's going to generate a bunch of the output. So you want to see like all the output from when you execute the command. If you use the double percent capture, it won't show this. Okay, so you will see here right now it's going through to execute. And if you already know Python, you probably understand what this one is doing. So pip install basically is install the packages from Python packages. Think about like your iPhone. You're going to an app store to search and then download and install on your iPhone. So this is the same idea. Is using the pip and to install, these are the package names. So install a bunch of packages. And after that, you might see this one here, for example, restart runtime. So because sometimes the computer already have some packages pre-installed. So if you install some new packages, sometimes there might be some conflict. Just think about this one as when you're using a Windows computer, you are installing some software, and sometimes Windows asks you, or you need to restart your computer to take effect. Okay, it's the same idea. So you can click just restart, and the runtime is restart. You might, if it is restarted, you might want to go through this one again, execute again, because when you restart the runtime, sometimes those variables are clear, in the memory is clear, so you want to re-execute. And I can control slash again right now to show you, right? I can install again, but right now you don't see any output. So this is a way for you, if you sometimes it gets messy, you want to hide the outputs. Once we install all the packages, the next one is to import the libraries. So you will see we have a long list. We use a lot of packages just to make it. If you, by the way, if you're trying to run this one on your local computer, you might need some additional packages. The reason we're using Google Colab, because Google Colab already pre-installed some packages. So for example, GDAL, and that one is, you might be having a difficulty trying to install on your local computer, just that you know. If you want, I can. So right now we already installed the packages. So next one, if you're trying to figure out like what kind of package is already installed, you can also do that. So put your cursor right now on this line, and if you click call, we can create another call block in here, and you can put exclamation and then pip, lowercase pip, space list. This one will show you what kind of packages already installed within this cloud computing environment. So if you, once you type this one and then hit this one, it's going to show you a list. If you go through, this is a huge list. For those use machine learning and deep learning, you will know that TensorFlow. So this is very powerful because you can run all kinds of complicated algorithm within the notebook. So there are a lot of packages already installed within this Jupyter Notebook environment, just to let you know. If you don't want to see the output, you can clear the click this icon on the left side here to create the output. Okay. So once we install the packages, then we're going to import the package to this notebook. So execute. And since this is the first time we are executing this notebook, it's going to, because later we're going to use the white box Python package to do some spatial analysis. So it's going to download the software and execute the other one. Then we're good to go. So basically right now we have already set up the environment, all the packages required for this exercise. So next, step 4, this one is optional. So we don't need to do it right now. If you can also click the icon here on the upper left corner to mark the Google Drive. It's the same. And next, let's go through the step 5. And so this one is trying to download the project data. If you see from here, the project root directory, right? If you go back to the very beginning. So the root directory, this one is the CDA watershed. If you use that for other watershed, you want to change this name because this name is very important. It is going to be, it must be the same as your sweat model, the zip file. So if you use other watershed, make sure you get this name and then replace it here. Okay, and so this is going to create the file. If you execute this one and the other one. So pay attention to the left side. Right now we have nothing in here because we haven't downloaded anything yet. But once we execute this one, it's going to download the Google file, the file from the Google Drive on the left side. Once it download the zip file, it's going to unzip the file. And later you want to see that on the left side, you want to have a data folder. Okay, so it's already in here, the upper left corner. And when you click, right, we have this file. So this is the file we downloaded from Google Drive, and then it's unzipped. So now you will see this directory. So this is the one that we saw earlier at the beginning. Okay, the same directory from this one. So now we have this file, and what else? So next, we're going to show the file because this is a watershed. It would be nice to see it on the map interactively. So this is the next few steps is basically to create a file and then display it on the map. So you can execute. So the first step basically is going through the directory. If you see from the file path, so everything here, single quotes, content data, and then the name of the project folder, and then the watershed shape and subbasin one. You can simulate on the left side here. You can go through the notebook, and if you go to watershed, right, shapes, and then subbasin one. So it's same from here. So this is basically a directory, and the second block is basically use GeoPandas to open the file. So it's a swap file. We can use GeoPandas to open and then convert it to a GeoPandas data frame, and then we can display the data frame on the map. You can also mosaic, basically merge all the subbasin into a single one, and then to create a boundary for the entire watershed, and then you can display it on the map. Okay.
Dr. I have a question. So basically, we are not writing the codes. The codes are already there, right?
Yes.
So what if I tried one model. Now I'm done with the first model. Now I want to try another model, for another watershed. So I don't have to edit the code, right?
No, everything is automated. So all we need to do is this three lines. Everything else remain the same. You don't have to change everything, anything. So I will automate the process. The reason that we define is variable because later we're going to use this name, whatever name you put in here, and then you're going to go through the directory automatically. So
thank you.
And next, we're going to get the boundary. So once you convert this one, we're going to get a boundary because later we're going to keep that in mind. We have the watershed, but we need to go online to download the DEM, download the NALCD. How do we know? Because we need the minimum bounding box of this watershed. So this code block is trying to figure out what's the bounding box, the coordinates, longitude and latitude. So if you click, it will show you here the minimum x, maximum x. So basically, x is the longitude, y is the magnitude, the latitude. So lower latitude and higher latitude. So the bounding box. And you can also get the center. So if you're trying to display the map, think about here when you're trying to create a map interactive, it can be global scale, but your watershed might be very small. So you want to zoom your map to the center location. So this one calculates the center location. So you have the minimum bounding box. So the average in between, that one is the center point. Once we get the bounding box and the coordinates, then we can read the data, the boundary, and then we can create a map. So we are using the Folium Python package. You don't have to worry about it, just execute. And we are also going to add the base map from Google. And this might take a couple of seconds. But once you execute this a few blocks, you want to have the map interactively. So we can look at where the watershed is located and also different data layers. Okay, so now you should be able to see the map. Any issues? If you run into issues, just unmute yourself, and then we can slow down. So just want to make sure that you get the map before we move on. On upper right corner here, you can see the layer control. So you can turn the layer on and off. So you can, for example, I turn all the layer off. So by default, this is the base map from OpenStreetMap. I also add the other one, the Google Satellite. So this one is useful because if you're working on watershed, you might want to see where the water are, and it's better to see on the satellite imagery. So this is where this code block is doing. Define the Google Earth engine, not Google Earth engine, Google Satellite base map, and then you can add everything to the map in here. Let me zoom out and turn this again. Where is it? Okay, in here. So the first layer is the subbasin. As you can see from here, we have overall 95 subbasins. We also have the river, right? And the entire basin. So keeping in mind, the first one and the second one come from the sweat model, the zip file. And the last one here, the basin is I created using the source code. So this one is not within the file. If you see, scroll your left side to see the folder, right? So the subbasin one and the river one. So this is already created. The outline, this one is created on the fly. Any issues?
Doctor, do you want to take a break for a couple of minutes?
Yeah, okay.
if you want.
Yeah, I can. Yes. So if you have any questions, you can ask questions. So we're gonna maybe take a break for 3 minutes,
Yes, we'll be
and then
back.
we can continue.
Yes, we'll be back around 11:20.
You can type your questions into the chat box, or you can unmute yourself to ask questions. Again, if you want to customize to some other watershed, you don't have to change the source code. You only have to change these 3 lines of code. So get your project zip file and get the floodplain, upload to Google Drive, get the share link, and then paste, overwrite the links in here. And also make sure you change the project name. Everything else is automated, so you don't have to go through the source code step by step.
Do you want to start?
Okay, let's continue. So earlier we already went through 6 steps to grab the data and then put into download the data to this notebook. And so the next 5th step, we're going to go through how to download the data automatically. Earlier in the PowerPoint slide, we already showed you that we need NED, the National Elevation Data Set, to delineate the depressions and stories. We also need the NLCD, the National Land Cover Database, to calculate the floodplain roughness and floodplain width. So step 7 is to download the NLCD data. Again, we already download the data from the internet and then upload that one to Google Drive. So you don't have to download that one by yourself. And this is the URL. If you like, you can click the link and to open this URL. So this file is almost 2 gigabytes. But keep that in mind, when you unzip the file to your computer, the raster is going to take almost 16 gigabytes. So it's much, much larger file. And this one so far is the most time consuming part. Download the file and unzip the file to this notebook. It can take a couple minutes. But for this exercise, I simplify the source code a little bit. So basically, I already create this the NFCD for this watershed, and I'm going to directly use the one. But if you use the other watershed, if you, for example, in here, you change the name, it's going to download the data and then unzip the file and then click the raster to just extract the NLCD for that specific watershed. Okay, so just execute. And we define the file path on the left side here. Right now, if you see the data folder, we only have the CDA folder. We don't have other folders yet. But once we execute this one, it's going to download the file and then unzip. You should be able to see this one sorted here on the left side. If you don't see the file, you can click the icon here, the one in the middle. So refresh, and then you should be able to see the file here, NLCD, right? And then you can unzip. You should be able to see this one. So NLCD 2016, and also you see the IMG file. This one right now is just for this watershed. But if you change again, if you change the name of the project, it's going to download the entire NLCD for the continental US. So that one is much, much larger. It's going to take maybe 5 to 10 minutes. So just that you know, if you're trying to run it for your own watershed. So once we have this NLCD, National Land Cover Database, the next one is to extract the data just for that watershed. So because we don't need for the entire watershed, it's much larger. So this line of code looks very complicated, but you just need to execute. You don't have to worry about that right now. So basically, we're trying to crop the imagery and to get the data just for that specific watershed. Once you get this one, you can refresh. And now you should be able to see this one on the left side here, NLCD.TIFF. So this is the one just for the CEDA watershed. And again, right now it's just a file. You cannot just double click to open that one on your computer. You can download that one. If you want, you can click the 3 dots here on the right. You can click the download. So I think this one is only maybe 40 megabyte. You can click the download if you want. If you want to show some metadata information, you can, again, Control/ and then execute this line to see some basic information about this file. So you can see here, the driver is using GeoTIFF. The size, so this is size, this is basically rows and columns. So how big is the raster? So with 6,011 rows and then 73 oh no, this is column. X, this is Y. So X, this is like how many columns, how many rows. So you can also see the coordinate system. So using the elbows equal area, upper left, upper right. So anytime if you already have some GeoTIFF on your Google Colab, if you want to show the information, you can use this command. So exclamation g.info, and this is the file path. So if you see from here, NLCD content, content folder, data, NLCD, and then this one. So you can change it to other files if you want. Okay, so for example, I can click here. I can copy the file path I can come back to here, I can paste, I can replace this one, right? And then you control slash again, you can get the same thing, but it's different data set. So this is just to show you the properties of the image. Okay, so we already automated the process to get the NLCD for any watershed you want. And the next one is to get NED, so the elevation data set. Similarly, we are going to create a folder called NED, right? So for now, we only have NLCD. Next, we're going to create the NED folder. And as you can see from the map in here, different from the NLC, the National Land Cover Database, we only have a huge file cover for the entire US. But for the NED, it's different. It's like tile by tile. So that's one small piece by one small piece. So in this example here, we need to figure out how many small pieces we need. We are not going to download the entire NED because it's just not possible. It's going to take a while. So we need to figure out the bounding box. So earlier we already calculated the bounding box. Using the bounding box, we can figure out like how many tiles we need or specific tiles. And then once we get the image tile, then we can mosaic them together. Then we can do the cropping to get the NED just for this specific watershed. So if you go back to here, right? So this function define a function in here to based on the input. Like if you give me a bounding box, I'm going to tell you what kind of NED tiles you need. So execute, and then so in this case in here, we're just going to print out how many NED images you need. So in this case, we need 9. So you hear north and the west, and then 44 row and column number. Once we figure out the ID, then we can download the NED automatically to this notebook. So how can we figure out? Because all the NED right now, the data is stored on the Amazon Web Service. So you can see from here, this is the URL that you need. And they have a specific file pattern. So if you see from this one here, if you see like curly brackets and this one, so this is where we pass in the number. So if you see from this, you can copy this thing to the browser and then replace the curly brackets with the ID. You will be able to download the file directly from the Amazon Web Services. So for example, I can copy this one. If you want, I can show you like what it looks like, right? And then you also need to copy one of the ID, right? Come back to here. And then from here, I can change this one and also change this one, or make sure you have a dot. If you hit enter, it's going to download the file to your computer. So once you hit enter, you will see here, you will pop up on your browser, and then you can download this one to your drive if you want. So this is a way for you to download the data automatically. And again, we have 6 images we need to download. So we're going to create a loop, like download one by one. So you can see from here, if you execute, it's going to download like processing because we have 9. It's downloading the first one. And on the left side here, you will see the folder NED, right? And you will see the file automatically right now are being downloaded. So 1 to 9. And this data set are stored on the Amazon cloud computing and different from Google. So it's going to take a longer time. If the data is in Google, it will be usually instant. But it won't take long because the files are not very big. So, and in this case, we're going to have 9. So if you see from here, basically you can subdivide this one into the watershed basically into 3 rows and 3 columns, right? And then one by one. And later we can mosaic the entire all the files into one single image, and then we do the cropping. Okay, almost done. So the next step here is to create a virtual mosaic. So this one, basically we're using the GDAL utilities. Again, if you see an exclamation and then GDAL, so those are the using the GDAL command. And if you don't see the exclamation, those are Python. So just think about here, this line is basically a command line. If you're using Windows, you can like type your CMD and then open the command line. You can type writing some commands. But if you use Python, you need to write Python source code. So those two are different. So we basically use a combination of two. Okay, so now we already have all the data. So you see on the left side here, we have 9 images altogether. And so the next one, we're going to create a virtual mosaic, basically mosaic all the data together. And then we convert this one to a GeoTIFF. So execute, right, very quick. Then convert the virtual mosaic into a GeoTIFF. And this one is going to take some time. You will see here from the output here, the file size is 30 or more than 32,000 pixels. So it's a much larger file size. I forgot to mention, so the NED here, we're using a 10-meter resolution NED. So 10 meter, not 30 meter. And once we do the mosaic, we're going to reproject because the NED is using a different projection from the NLCD. So we try to combine all the data set, but we want to use a consistent projection. So everything we're just going to use the NLCD. So we use the NLCD as a template because it is using the equal area. And then we're going to convert the NED also to the same projection. And then we can do the analysis together. Okay, 70%. Also on the left side here, if you see my cursor here, lower left corner, you will see the hard drive, right, decreasing because we are creating the file and store here within this notebook. So, but we have 100 gigabyte, should be sufficient for this exercise. Okay, we have finished the creating the mosaic. Next, we're going to do the reprojection. So click this one. And again, it might take a couple of seconds, but you will see the process. Once we finish this step, we're going to have a file called ned.tiff. So right now it's not there yet, but you will see here earlier we created mosaic.tiff. So the mosaic is all the files right now here, 9 images, NED images, mosaic together into this one. And we also have the NED. So if you refresh, okay, so we have this one. So this is the NED, right, for the entire watershed, but it's a rectangular area. And so the next step is to do the cropping. So we want to crop this one just for the watershed. And as you can see here, you can click. It's going to just crop. And then at the end, we're going to have the other one called dgm.tiff. And that will be the final one. Okay, so it's done. Refresh again. Now I have this one. So after this two steps, basically right now we have the NED, right, NLCD.tiff, and also DMTIFF, right? Everything is automatic, so you can change it to any other watershed. Again, if you want to see some metadata information, you can Control/ and then Control Enter to see this one. So if you see from here, GeoTIFF, right, the size is 60117383. You'll be the same as the one that we used earlier. We come back to here. So now these two images are at the same projection, same size, same configuration, so that we can move on to calculate the floodplain roughness and width. Any questions so far? If not, then let's move on. So the step 11 is to download the floodplain data. So this one comes from here. If you go to the very beginning, this line, right? So earlier we only deal with the project, the SWAP data model zip folder. So next we're going to extract the raster, the floodplain raster. So come back to step again. You can use the table content to navigate. So step 11. And so in this example here, the floodplain, we can download the data. So you can execute, and then let's look at this one. Now it will create a folder on the left side, and it's called floodplain. As you can see from here, this is the specific CEDA watershed, and you might, depends on your different project, the name might be different. So the reason that we have a few lines of code in here is to figure out which file to use. Okay, so in this line, basically we're going to searching the entire folder, find out the TIFF file, and you're supposed to only have one TIFF. So, and then we figure out this name. So we're going to basically use the program to automatically figure out the name of your floodplain. Okay, so if you see from here, you can execute. As you can see from here, right now we figure out that okay, the file name is this is the file path. Later, because we need this file to calculate the floodplain stories. Okay, execute and then execute. This one might take a while. It depends on the project. Let's see. Okay, so it's taking if it's taking a long time, on the left side here, you can click this button. So let's stop this one because I already generated the. We know that this is the TIFF. That we already know the name, so we can directly just use the original one. Let me copy this one here. Oh, probably I forgot to change the code. Let me 1 second. Let me copy this one in here. If you're having issues, you can click the link in the chat box. Open that one. I'm going to update right now so they can get the most updated one. And let me go to step, I think number 11. Yeah, it's be the same. Okay. Okay. Anyway, just forget about this one and move on to step 12, because in this case we're just going to use the original floodplain, the name in here. See the underscore FP. But if you use other project, it's going to use this line to automatically extract the floodplain for your area and to convert the projection to the same as the NLCD, right? Because you have the data set from different sources. Sometimes if the projection is different, you might have trouble computing the source code. And so far we have created the NLCD, the NED, and also the floodplain. So those are 3 data sets that we need to do the computation. And now we can move into step 12 to calculate the floodplain meaning. So this is basically the floodplain roughness. If you go back to the PowerPoint slides, and we scroll to the here, right? So we need the NLCD, right? The data set that we already extracted from the National Land Cover Database. Then we're going to crop the data just to the floodplain. So we also have the floodplain layer, right? If you see from this one here, this is the floodplain raster. And we only extract the NLCD within the floodplain. Then we do the recoding, reclassify based on the lookup table, and you get a roughness. So let me come back to the source code in here. So this code block in here essentially is to do the computation to reclassify the image, and then at the end generate the file that we need. So this is the output that we need for the model. Again, you can click. So this code block in here is basically doing the reclassify. So if you use ArcGIS, you might be familiar with something like this. If it is equal to 11, you're going to change the value. So, and at the end, we're going to do some zonal statistics. So this one is doing the zonal statistics because at the end, we want to aggregate the result for each specific subbasin. So in this case, we have 95 subbasin. So for each subbasin, you want to have the floodplain within that subbasin. You want to have the NLCD. So we reclassify and then aggregate the result, get the total area within the total floodplain area within that subbasin. And come back to here. Take out this execute. And later we're going to create a folder called output. So right now we don't have the folder yet, but it should be there very very soon. So execute, and we're going to read the data and do the zonal statistics. So for this few lines of code basically is trying to calculate the river. Okay, so because when what we're trying to do is calculate the floodplain. If you come back to here, or this one here, okay, the floodplain and also the river. If we're trying to calculate the floodplain width, then we need the total floodplain area within that subbasin and also the total stream length, right? And then you use the area divided by the length, you get the width. So this is how we calculate in here, get the river length, and then we're going to calculate the width for each subbasin, so one by one. So we're going to go through. This is basically a loop, and you can just simply execute. So lastly, we're going to have the file in here, right? Floodplain width and roughness. On the left side here, refresh. And now you should have this output folder, right? We have two files. So this, we need three, right? Well, we already have two. So the floodplain roughness, width, and also the floodplain roughness. So you go back to here. So basically what we did earlier, just to figure out these two, okay? Subbasin by basin. And then, so the first one is the floodplain area divided by the river length. So you get the average width for each subbasin, and also the roughness, right? So the NLCD within the floodplain, do the recording, and then use zonal statistics to calculate the average roughness. And this is what it looks like at the end. You can go back to the beginning in here, these two files. So this is what it looks like when you download the file to your computer and when you open. So you're going to have 95 rows, and each number represent. So this is meter, okay? So for the width, the unit is meter, and this is the roughness. Any questions? Can you all execute the source code successfully? On the left side here, if you want, you can click this one and then download. Okay, you can download this one to your computer, because these two are just small TXT files, so it should be pretty quick. You can download this one to your computer. Okay, so the last part is to delineate the depressions and calculate the water storage. So what we are trying to do is to get this one. Okay, we already have these two. So this will be the last one we're going to get. We're going to have 5 columns and 95 rows for this specific watershed. Okay, so in order to calculate the depression, we need the DM, right? So earlier we already generated this DM. So it's called dm.tif. You click this one here, it'll be this one. And there are some parameters you need to adjust. So the first one here is the minimum size. The minimum size is basically when you're trying to delineate depression, you need to define how big, what's the minimum size. For example, it might be just, some of the depression might be just 1 pixel, 2 pixel. If you don't want like too many tiny depressions, then you can define a minimum size in here. So the minimum size is the number of pixel. In this case, we use the NED. So we sample the NED to 30-meter resolution. So 10 pixels. So 1 pixel is 30 meter by 30 meter, 900 square meter. So 900 square times 10, basically 9,000. So this is almost like 1 hectare. So that means we want to delineate depression, but we remove those small ones. So this one, it can be customized. It depends on your specific application. You can change this one to a larger number or a smaller number. If you want a lot of a smaller depression, you change this one to smaller. If you just focus on large depression, you change this one to larger. For example, maybe we can just do 100. So in this case, it will be 100 multiplied by 900 square meters. Okay, so execute. And this line of code is going to delineate the surface depression. So the package is called LiDAR. So this is the one I developed, and you can just execute this line of code. It's not take very long. So it's going to load the DM, and then based on the minimum size you define, it's going to create a folder, a download folder. So on the left side here, if you go to output, if you refresh, now you should see the depressions folder. So everything is automatic. As you can see from here, we have a bunch of files in here, the DEM and also the reason. So the reason, this one basically is just the maximum depression boundary. If you want to delineate the depression hierarchy, you can you can do that as well. But in this case, we're just going to get the minimum, the maximum depression boundary, just to get the water storage, the potential water storage. And if you want, you can go back to the PowerPoint slides to look at what this one is doing. But I'm going to just quickly go through the process. So this one is local using the level set methods, right? So think about here, this can be a depression, right? This can be also a depression. And depends on the water level, the depression might, like water increase, depression might merge together into large one. When the water level decreases, depression might split into two or more smaller depressions. So if you look at from the left to the right, basically you can see the depression or the surface water are shrinking, right? If you see from the right to the left, right, these three shapes, the water level increasing and depressions are merging, right? And this is how we actually use this algorithm to delineate the depression hierarchy. So rather than trying to explicitly simulate the shape changes, you can move like just a plane and then cut through the DM and then move up and down. So this is basically an implicit way to simulate the process. And it's called level set. You can look at the source code if you want. And this shows you a diagram like how this one is doing. So simulated, but like if you see from this one here, this is just like a DM, and the profile, you will see that there are multiple depressions within this bigger one. So the idea is that we flat the depression like to the maximum level, and then we see the water level decreasing. As the water level is decreasing, you can see that dramatically that depression is going to split into multiple depressions, right? So from the here, A and A is still one big depression. And at this point here is critical because they become smaller depressions, and then you will see the water will keep decreasing until the end. The landscape is totally dry. Then in this way, you keep check all the hierarchy, and on the upper right here shows you the hierarchy, right? So essentially, this big depression has a hierarchy. Okay, the big one on top is A, and you have B and C, and B can further continue to be split into D and E, right? So depending on how complicated your landscape is, the hierarchy can be very deep, right? You can have multiple hierarchies, right? So and then you can also delineate the area, the volume, the depth, also the spill elevation. All the information will be stored within the output. So we tested this one in the Prairie pothole region. You can see from the example like this one. We use the bathymetry DM. So you can look at this one here, the lower right corner. So this is what it looks like in the area imagery, right? You can see this is a big depression complex, and this is just one depression. But when the landscape is dry, actually they're separated into multiple depressions. So you can see from this one in here, okay? And if you're using the traditional methodology to delineate depression, you're going to get a big one, but you don't know how many small ones actually inside. So using this methodology and also the bathymetry LiDAR DM, you can figure out the hierarchy within there. So and you know exactly, for example, they say these two depressions, P2 and P4. When the water level increase, when you have sufficient water, you will know that these two depressions are going to merge together and then form a larger one. So basically, you have the relationship between your upland and your downstream. And once this one is fully filled, you will know that where the water is going to flow to which downstream. So you have the entire network that you can delineate. And lastly, this is what you can get. Excuse me. So you have all the depression. You also need the detailed information, the hierarchy, the area, the volume, the depth, and also the spill elevation. So you can also, for example, you will know which depression are nested within the larger depression. So you can get all the detailed information using, excuse me, using this algorithm. In this exercise, we only use the maximum. We don't go into the hierarchy, but just let you know, you can get all the detailed information. So once we have the depression, so the next is to calculate the depression area and volume for each subbasin. So because in a large area, sometimes you might have some huge depression that cross multiple watersheds, multiple subbasins. So in this example, we need to cut those, basically intersect, cut some of those larger depression into small ones. So it only, the area that we get only contains the depression within the specific subbasin. So this is how we calculate. Again, yeah, you just skip, I just go through execute. And this one shows you like how many depression right now within this subbase, within this basin, Cedar watershed, right? For example, we have more than 1,000 depressions. If you change the minimum size to a smaller one, you want to get a larger number of depressions. So just be aware. And then we can use the excuse me, the intersect. Like I said earlier, right? You have a larger depression cross multiple depressions, multiple subbasins. You want to just cut that smaller one and then calculate the percentage area, and then use the percentage to calculate the percentage volume, right? And then you can aggregate all the depressions within that subbasin to get the area and volume, and then we can get the final results. So the WBT is the white box package, white box library. And if you have a larger number of depressions, this might take longer. Okay, so it depends on the specific file you're working on. And the next few step is to grab the information. So there's one here called reason.info.csv. So this CSV contains all the statistical information, the area, the volume, the depth, the size, the spill elevation, everything is in here. And then you can join this table to each individual depression. So the depression only contains the sweep, and then you can join the information. Once you have this complete file, then you can do the intersect with the subbasin, and you can calculate the zonal statistics. Okay, and so execute, and this shows you that in this example, we only need the area and volumetric information. So if you see from here, right, we have 1,275 depressions. So we get each depression the unique ID. We also get the depression area and also the volume. So this one right now is already being we get from the labels algorithm. So these two, and then we're going to merge this one, and then we're going to keep using the intercept because, as I said, some of depression cross multiple subbasins. And execute. You can control slash to show the data if you want, but I'm going to just skip through to show you the final output. And then lastly, we're going to merge this one to the subbasin because each subbasin has a unique ID. When you use the intercept, you can figure out like which depression are located within this with the subbasin, and then you can use the ID to compute the aggregate results. So execute. And now you see here, this is the final one that we need for each subbasin, right? So you have a subbasin ID, you have the depression area, so it's already aggregate all the depressions within that subbasin, and also calculate the volume for the subbasin. And this will be the basin area, right? This is just from the geometry, the basin subbasin area. And the last one is the depression, the total area of depression divided by the total basin area. So we can see from this one here, so some might be 10%, some might be only 1%, so it varies. And lastly, this is a GeoPandas data frame. Then we can save this one as a CSV. So you can see this is the last code block that we need. And we can come back to here, refresh. Okay, so now you should be able to see these three files that we need for the model. And the floodplain width, roughness, and also the subbasin area and volume. And if you go back to here, right, this is what we said at the beginning. We're trying to delete these three files automatically, depends on whatever watershed you are interested in. So everything is automatic, and you don't have to write the code by yourself. The only thing I want to point out is that you can customize, like I said, you can customize the minimum depression size. Depends on your specific interest. So you can change this one. Oh, where it is? Let me go back to here. Step 13. So step 13, change this one if you want. Otherwise, you can, everything else is, you can use the default settings and then only change these 3 lines of code. That's it. Okay, that's all for my demo. If you have any questions, I'll be able to take any questions.
Question from the audience? We have time. We have other 2 segments to talk more about this. Dr. Thank you so much. I mean, it has been very helpful and very clear. Just a quick note: if you want to use a different model, you don't have to write anything. To be honest, Dr. Wu had to go step by step to explain what is going on with the code. If you want to use your own SWOT model, you just have to make change in one place. You just have to upload your SWOT model in your Google Drive, get a shared link and paste the shared link in the code and then run each steps. That's it. You don't have to change anything. It should work. Now, we talked about data discovery. The data sets for our test model is ready. Now changing, she's going to demonstrate how this data set is now going to be fed into the model source code. Changing.
Hey Anand, let me, I forgot to, let me just do another quick
yes, please.
demo.
Yes, please.
So I already went through step by step, right? So earlier I mentioned that you can run all at once. You don't have to go through step by step. So now I'm going to show you like how you can do it quickly. If you go to the beginning of the source code, so all you need to do is to go to this code block, green line here, control slash. On the left side here, right, we have a data folder. So if you execute this line, it's going to delete the entire folder and then you can start from scratch. So I'm going to execute this line and the folder should be gone now, right? And let me control slash again to comment out this one. And after you did this, go to edit, clear all outputs, right? And once it's clear now, you will see here no outputs there. And then all you need to do, you can just try this one, restart and run all. So you will basically start from scratch, but this time it's using the automated process. So all you need to just hit yes. And now you see here, it's going to go through automatically, right? And you see like executing step by step. You see the spinning, right? When it's done, it's changed to the a number, but it won't take long. So this maybe just take a couple minutes and then you get all the result automatically. The most time consuming is to download the data and that's it. Everything else pretty much won't take very long. Okay, that's all.
Regarding the runtime, we tested for the watersheds, and you can see, you can go back to the slides for a large watershed in central Indiana, which is 18,000 square kilometer. From start to finish line, it took around 18-20 minutes. So it's very fast. Stella, she's going to demo the model integration part. Now the data is going to be fed into the SWOT model. So we have wetland and depression storage, we have floodplain extent, and the floodplain roughness in hand.
Okay, did anyone can see my screen?
I see your screen, yes.
Okay. So in the previous section, Dr. Wu showed us the process of data discovery and the calculation of depression and floodplain storage. Now you can find the output file on your left panel, the CSV file, floodplain width, floodplain roughness. Now, with holding these data in hand, the next question is, how are we going to integrate these pieces of information to our model? Let's go back to our SWOT model. So this is our SWOT model. We know the goal of this project is to update the depression storage in the model input files. But how? It is possible to do it manually. For example, the Cedar watershed we are using as example. It's only have 95 subbasins, so it's okay. You can do it manually, and when you have small watershed. But however, if you are working on a major river basin with thousands of subbasins, for example, Mississippi River Basin, thousands of subbasins, then it is unrealistic to type in one by one. So you have to type in one by one. It can be done, but it may take years to finish. We don't know it, right? It's a lot of work. Also, manually update these parameters will increase the concern of causing human error, such as typo. For example, it should be like 100, but I mistype. I typed 1,000. It will reflect your results. And picking the wrong file. For example, I want a subbasin 35, but I accidentally opened 36. So you got the wrong things to match up the files. Also, you are missing some files. Maybe you did like 500 already. You are tired, and you thought you already did 501 subbasin typing, updating the data, but actually you are not. So you're missing some information. So we are saying the Cyber-enabled tools might be the good answer to integrate these data to our models. So now let's run our code. The data we prepared in the CSV file has the unit in cubic meter, which is different from the selected parameter in the SWOT model. In the SWOT model, the hectare will be the correct unit. So the first step, we're gonna convert the unit of depression area and volume in the SWOT format. So we run that. So now you have updating the new CSV file, which is ready to integrate the depression data with your model. So after converting the unit, we are actually integrating the data into the SWOT model. The SWOT model input basically named by the ID, as I showed you before. So the ID number from 1 to 95 for our Cedar River. So we need to get a list of these subbasins first. Then we search the input file based on the ID number. Once we located the input file, we match the name of the parameter with the header of our CSV file. And then we were updating the data with our calculated one. So now second step, we integrate depression data with our SWOT model. After run this, refresh, you will see you have updating the files. Now you have all the file in your hand. Once we finish updating the parameters, we copy the file I'll copy the and floodplain width, floodplain roughness under the file to the text in and out subfolder under the scenario folder. So after integrating this data into a SWOT model, now after integrate this, now you're ready to zip the modified SWOT project folder and download to your local machine. So it will take a little bit while if your project is bigger, as we said before, the area is bigger, you have a lot of information there, then it will take time. It depends. But you already see the Cedar news, the new modified SWOT project folder is ready here. Okay, now let me. Okay, see, it's in the processing. So after we download it, finally, your new SWOT model is ready to run. But before we run the model, let's check something, okay? Let's open the files to check our work if it's correct or not. So these files stores information that control wetland simulation in the SWOT model. So after this is the original one in your SWOT model. And this is the update in the file in your SWOT. Okay, so now you can download it. Download it to your local computer. So you can see there, after the data integration, you will find the parameter have been replaced. They are different. See, here is all 0, but here we got our surface area, volumes, depression, maximum area, and maximum volumes. Okay, so now you're good to go. Now you can run your new modified SWOT model to get your new result with those all the depression information and the floodplain information. Okay, so if you want to try your SWOT model, your own SWOT model, once again, simply replace the project zip file and the floodplain zip file URL and the project name with your own Google link and project name, which we mentioned in the really earlier, just this 3 line, simply just 3 line. So I have another example here. So everything exactly the same. The only thing different is just 3 line. Take example for Salina Watershed. So I only change these 3 line and run all the steps, and you all got a new one, new SWOT model folder for your new project. And you are doing the same thing when you finish everything, finish running all the code box. You just need to zip it and download to your local computer. Then you may rerun your model to get your new result. That's it. That's all. You don't need to worry about the rest of the code. And that is the part of the data integration. Any questions?
So basically, you read the files generated by Dr. Wu's data discovery portion and put it in the model. Right?
Correct.
So what if there is a problem in one of the CSV files that the data discovery code developed? If there is one subbase missing, what happens?
Oh, actually, the code is automatically. If it's missing, because as I mentioned, first you will get the subbasing list, and then you will have the list in the Dr. Wu's CSV file. If they will match both of them, if you don't have, then they will escape that part. So you won't have any trouble, either you missing any subbasing number or not.
Okay, got it, got it. So, Dr. Ru, should we move on to the next segment? Thanks, Stella. I appreciate it. Dr. Ru, should we move on to the next segment?
Yeah, if we the parties may have any question, we can answer any questions right now.
Yes, yes. Guys, please share your questions if you have one. I have one idea. I wanted to take a picture of screenshot of the participant, because these are strange times, right? Because we can't see you, but we want to take a screenshot. Right now I can see your names only. So if you want to turn on your camera, that's good. If not, we just want your permission to take a screenshot, just to share, to share in LinkedIn or Twitter. Wonderful. We have Brent here. Okay. Dr. Ru, do you want to take a screenshot? Oh, Gray, I see Gray here. Oh, Jeffrey. Wow, good. Let's wait for a couple of minutes. Everyone is active.
Oh.
Wonderful. Because we have been doing all these Zoom meetings in last few months, and this last week I used 5 different platforms. So it's 5 different platforms with hundreds of faces. So it's very difficult, So we wanted to keep this memory. Dr. Ru, I think we can take a screenshot.
Yeah, I already take a couple.
Okay, nice, wonderful. Oh, we have more people showing up. I can see people in the cornfields, which is good. Okay.
Yeah, I think I have plenty. So
yes. Okay. Now we are in the final two segments, and this is going to be interesting because this is where you are going to run the show. You are going to teach us, and you are going to talk, hopefully, and you are going to tell us what is it that you need, how we can be more helpful. Now, let me share my screen because it involves a little bit of hard work. Sharing screen. Here we go. Sharing screen. Okay. So we already shared the code and shared the PowerPoint with you. And we want 15 minutes of your time to fill out a survey. Now, this survey is different. We are not going to ask you whether you like our approach, what you learned. No, we are not going to ask these questions. You'll see that there are some technical questions, not so difficult technical questions though. There are some technical questions. We wanted to capture your inputs about processes, with how we can improve our process, and whether or not you like a graphical user interface, because you can see from our presentation, this is raw codes. Although the code is very stable, you don't have to write anything, but still it's just a bunch of lines. Do you want do you want us to develop a graphical interface and things like that? There is question like metadata. Currently the tool partially captures some metadata, but do you want it to capture all the metadata for provenance purposes? So all sorts of things. Quick note, the survey is not anonymous because we want to share our updates with you, and because we are in the process of publishing the tool, we want to share the publication as well. So the survey is not anonymous. So please spend a few minutes with the survey.